Hi everyone. I lost internet right as I was writing these notes, so I'm just going to go from here. I didn't get very far. So welcome to the Math 111Z video lecture. We're going to cover sections 3.3 and 3.4, which is about rational functions. Starting with the definition, a rational function is simply one polynomial divided by another polynomial. X squared plus 1 over x squared minus 3, because that's one polynomial divided by another polynomial. You don't have to have the same degree in the top and the bottom. 7x to the fifth minus 13x squared plus 1 divided by 3x squared plus 9. That's a rational function. Or x plus 1 over x to the fourth minus 5. That's a rational function. Now, these three are kind of the classic that you tend to see, where they're very obviously polynomials in the top and the bottom. But there are others that are less obvious, like 1 over x. That's a polynomial because 1 is a polynomial and so is x. Same for 1 over x squared. And in fact, x to any negative power is a rational function because you can always write it as 1 over x to that positive power. Some things that you might think wouldn't count do, like 3x squared plus 7x minus 2. That's a rational function because I could just divide the whole thing by the number 1, and 1 is also a polynomial. And that means we can get really, really simplistic and say something like 3 is a rational function because 3 is 3 divided by 1, and both 3 and 1 are polynomials. So there are a whole bunch of rational functions out there. We are mostly going to focus on this type with a little bit of these ones. All right. Most of what we did with polynomials was where are the important characteristics? What are the important characteristics of a polynomial? And how do you graph one? And we're going to be doing the same thing for rational functions. So the important characteristics of rational functions, it's going to be very similar to polynomials. We care about the y-intercept. We like to know what our initial value is. We care about x-intercepts. We want to know when that function equals 0. We care about the end behavior. What does that function do as x goes towards positive or negative infinity? We don't care as much about turning points. Instead, what we care about are vertical asymptotes, places where the function value gets very, very big towards positive infinity or very, very negative towards negative infinity. And the last one is something called holes, or you may see them now or later as removable discontinuities. And related to vertical asymptotes and holes are the idea of the domain of a rational function. So let's break it down. A rational function is one polynomial divided by another polynomial. And if I write it in standard form, that could look something like 3x squared minus 7x plus 5, all divided by negative 2x cubed. Sorry, let's do squared. Negative 2x squared plus 13x minus 3. When you have a rational function in standard form, it's very easy to find the y-intercept because that's when x is 0. And if x is 0, everything drops out except the constant on the top and the constant on the bottom. 0 squared is 0. 7 times 0 is 0. 13 times 0 is 0, and you're just left with the 5 over negative 3. So f of 0 is 5 over negative 3, or we might write that as negative 5/3. So the y-intercept is 0, comma, negative 5/3. The y-intercept of a rational function is the ratio of the constant terms. That takes care of the first one. I think the y-intercept is one of the simpler ideas working with rational functions. Let's skip x-intercepts for now and go to end behavior. Let's use the same function for this, 3x squared minus 7x plus 5 all over negative 2x squared plus 13x minus 3. And imagine you're looking for the end behavior, so you put in a really, really big input. Well, that means you have 3 times that really big input squared. And then you take off 7 times that big input, and you take off 5, or you add back 5. And in the bottom, you have -2 times that really big input squared, plus 13 times that really big input, and you take off 3. And now what we have to do is we have to ask ourselves what really matters. If I'm squaring a big number, like if x is 1,000,000, and I'm squaring 1,000,000, that's, I think it's 1,000,000,000,000. Yeah, that's a huge number. That 5 doesn't matter at all. That's not really going to change what the top looks like. And the -3 in the bottom doesn't really change what it looks like either. So I might as well just scratch those off. And in fact, the 7 times the big number, I mean, it's going to be big, but it's still going to be very small compared to when I square it. So really that piece doesn't matter either, and neither does the piece in the bottom. So when x gets very big, f of x starts to look like 3x squared over -2x squared, and none of the other smaller terms matter. And I can simplify 3x squared over -2x squared to be -3 over 2. So when x gets very big, f of x gets very close to -3 over 2. And this right here, the -3 over 2, is a horizontal line that guides the function as x gets big. That is a horizontal asymptote. So when we talk about end behavior, most rational functions that we look at, many rational functions that we look at, have a horizontal asymptote. The horizontal asymptote, if there is one, is completely determined by the ratio of the leading coefficients. The leading coefficients in my function are 3 and -2, and so the asymptote the horizontal asymptote is -3/2. That takes care of end behavior. To talk about x-intercepts and vertical asymptotes and holes, it's much easier to switch from the standard form to a factored form, because rational functions, just like polynomials, have factored forms. And the reason they have factored forms is because they're built by polynomials, and polynomials themselves have factored forms. So let's use an example. Let's do 2x squared minus 10x. I believe if I do a minus 28, I'm going to be safe. And divide that by x squared plus 8x plus 15. Now this is in standard form. By the way, I can tell you exactly what the y-intercept is. It's -28/15. And I can tell you what the horizontal asymptote is. It's going to be 2/1, or 2. If I want the x-intercepts, those are where the function equals 0. And a fraction equals 0. Remember, a rational function is a fraction. A fraction equals 0 if the top equals 0 and the bottom doesn't. All right, so 0/3, that equals 0. 0/-2, that equals 0. 0/0, well, that's undefined. That doesn't equal 0. So a fraction will equal 0 if the top is 0 and the bottom isn't. In the context of a rational function, f of x equals 0 when the top, 2x squared minus 10x minus 28 equals 0. But that is exactly asking what are the x-intercepts of 2x squared minus 10x minus 28. 2x squared minus 10x minus 28 equals 0 at its x-intercepts. So I'm asking, what are the factors of 2x squared minus 10x minus 28? Well, to find the factors, you factor it. We can pull the 2 out, and I get 2x squared minus 5x minus 14. And because of the way I worked it out, I'm pretty sure that this is 2 times x minus 7 times x plus 2. So that means the x-intercepts are x equals 7 and x equals -2. Those are the x-intercepts of the top, and so they're also going to be the x-intercepts of the whole function. Let's talk about vertical asymptotes. And the easiest way to talk about them is just to tell you where they are. Vertical asymptotes occur when the bottom of the fraction equals 0 and the top doesn't. So it's simply the opposite of the x-intercepts. These are the opposite of the x-intercepts. So our whole function, which was 2x squared minus 10x minus 28, all divided by x squared plus 8x plus 15. I want the bottom to equal 0, which means I'm going to factor the bottom, which factors into x plus 3 times x plus 5. So the vertical intercepts, or sorry, the vertical asymptotes are at x equals -3 and x equals -5. And holes, our last characteristic, occur where the top and bottom share the same factors with the same multiplicity. Now that hasn't happened in our function. I'm going to write out our function in factored form. Actually, I'll write it in standard and then in factored form. So f of x was 2x squared minus 10x minus 28 divided by x squared plus 8x plus 15. And when I factor the top, I get 2x minus 7 times x plus 2 divided by x plus 3 times x plus 5. Now, there are no factors shared in the top and the bottom, so there are no holes in this particular rational function. But I'll show you an example where there are. Let's graph it. Let's start by finding our x-intercepts and our vertical asymptotes, because that means finding the corresponding factors of the top and the bottom. 1, 2, 3, 4, 5, 6, 7. There's going to be an x-intercept at x equals 7 and an x-intercept at x equals -2. And there's going to be a vertical asymptote at x equals -3. We've talked about vertical asymptotes before. They're imaginary vertical lines that guide the function. And there's going to be a vertical asymptote at x equals -5. So we have x-intercepts. Check. Vertical asymptotes, VA, check. Let's put our horizontal asymptote in next. Remember, we just cover everything up except the leading terms. It's 2x squared over x squared, which is 2. So we're going to have a horizontal asymptote right here, 2. And that's our end behavior. Horizontal asymptotes are end behavior. So we don't have the little box like we did with the polynomials. Instead, what we have to do is we have to think about connecting these functions up. So I know that when my value gets very big, I should be close to my vertical asymptote. So let me just draw my end behavior is going to be pretty much a flat line, pretty much in line with that asymptote. I also know it goes through when x equals 7, and checking the multiplicity, it should go through like a line. So let me just do that. Go through like a line. All right, that's pulling back our polynomial skills. Now, what's going to happen next? Well, it's going to have to come back through x equals -2, so I guess it's going to have to turn around. And it comes through the -2 because it's like a line. And now, the next thing that's going to happen is it's going to approach my vertical asymptote. It's going to go up and up and up forever, never touching that vertical asymptote. after that vertical asymptote, I have a couple of options. I could say, oh, it comes down and turns around and goes back up. Or I could say it comes from beneath and turns around and goes back down. There's two ways to know what to do. The first is to memorize a rule. The rule is if the multiplicity of the vertical asymptote is odd, then the arrows switch sides. And now it comes up, it can never touch or cross the axis again, so it has to turn back down and goes down again. So that's one way to figure out, is to say, all right, it's an odd multiplicity, so it turns around. The other way is to just test a point. We could test right here, x equals -4, f of -4. Let's just try it. I'm going to use a factored form. 2 times -4 minus 7 times -4 plus 2 all over -4 plus 3 times -4 plus 5. So that's going to be 2 times -11 times -2 all divided by -1 times +1, which is 44 over -1, which is -44. That's a negative number, which means I have to be in the negative area, in the negative part of my y values, 4 comma -44. So you can either memorize the rule or you can test a point. I've come down here. I have to finish my graph over here on the left. I have a couple options. Again, I could think it comes up, but if it came up, it would have to cross through my x-axis, and I know it doesn't. So it has to come down, like so. And again, it switched sides because the multiplicity on the x plus 5 is odd. There's my picture. It looks weird. It doesn't have all the details. Well, I can put the y-intercept. That's super easy. Just cover that up. The y-intercept is -28 over 15. And that's my function. Rational functions look strange. They follow specific rules, but those rules can produce strange looking graphs. So you really have to focus on the rules to help you draw them. Let's just do a different one. Let's do another example, and then I'll talk about holes and also some special cases for end behavior. I'm not going to worry about the y-intercept for this one because I'm just going to give this formula to you in factored form, and I don't feel like multiplying it out. So let's do 7 times x plus 3 times x minus 1 times x minus 4. And let's divide that by 2 times x plus 2 times x minus 3. Okay. Let's start by plotting our x-intercepts. We have an x-intercept at -3, at +1, and at +4. And now let's plot our vertical asymptotes. X equals -2 has a vertical asymptote. X equals 0 because that x right there means if x is 0, the whole thing's 0. By the way, this is going to mean my function has no y-intercept because it can never touch the y-axis because there's a vertical asymptote there. And I'll have a vertical asymptote also at +3, like so. Okay. So x-intercepts, check. Vertical asymptotes, check. Let's do our horizontal asymptote. Cover everything up. 7 over 2, which is what, 3.5. So it's like here, even though I'm not worrying too much about my vertical scale. Notice the asymptotes cross. That's not a big deal. Horizontal asymptotes really only matter when you're way out on the sides, and you can ignore it everywhere else. So let's connect. Let's do it from the left side this time. I know when x is really small, I should basically be equal to 7 over 2. and I have to come down and get through that x-intercept. It's a linear x-intercept, so it goes straight through and it comes down. Now I have to decide whether I'm up here or down here, and I can test a point, or I can remember since the x plus 2 has a multiplicity 1, it must change sides, and since there's no x-intercept, it must turn around and run back up toward positive infinity, so it doesn't touch the vertical asymptote at x equals 0. Again, at x equals 0, it's linear, so it changes sides. It must come up through and keep going up forever because it can't turn around, because there's no place for it to turn around. And that confirms that it switches sides and then comes up and goes out, like so. All right. That formula was not so different. The picture is way different. Rational functions follow specific steps, but the graphs can look very, very different with very small changes to your formula. All right, let's talk about holes. Let's look at f of x. I'll keep it real simple. X minus 1 times x plus 2 divided by x minus 3 times x plus 2. Well, the first thing I would like you to notice is that when x equals 1 and when x equals -2, the top equals 0. And for the bottom, when x equals 3 and x equals -2, the bottom is 0. There's an x value that make the top and the bottom both equal to 0. And importantly, the powers are the same. The multiplicities of those are both the same. If this were arithmetic, we would cancel those terms because they're the same on the top and the bottom. But since this is algebra, we can't cancel them because when when x is -2, I have -2 minus 1 times 0 over -2 minus 3 times 0, which is 0 over 0, and that is undefined. So -2 is not in the domain, but when x approaches -2, the top and bottom balance. If I try f of -1.99, that's going to be -1.99 minus 1 times -1.99 plus 2 over -1.99 minus 3 times -1.99 plus 2. And these parts here balance. They're both 0.1, just those parts. And they're balanced, so they don't affect the rest of the function. And what that means is, let's see, when x is 1, my function is 0. When x is 3, I have a vertical asymptote. But when x is 2, the top and the bottom balance, and it becomes something very similar to -2 over -5. It's multiplied by 0 over 0, so it doesn't exist, but this should be -3 over -5. So when x is -2, my function doesn't exist, but it's very close to a height of -3 over -5, or 3/5. So my function will go right through here and then just skip and leave a hole. and then it'll come down like so. This is what we mean by holes, when the top and the bottom have the same factor with the same multiplicity. Now, if they don't have the same multiplicity, you might still end up with a vertical asymptote. But the important thing to recognize is sometimes your polynomials in the top and the bottom share a factor, and that can change whether or not you have a vertical asymptote. Okay, there's something similar that happens with end behavior, which generally is very simple. You just look at the ratio of the leading terms. So if I have, for example, 7x squared plus 1 over 2x squared minus 8, then my horizontal asymptote is just 7 over 2, because I just look at the ratio of the leading terms. But what if I have something like g of x equals 7x squared plus 1, but the denominator is 2x to the fifth minus 8? When x gets very, very big, this starts to look like 7x squared over 2x to the fifth. But when I reduce it, I get 7 over x squared. And 7 over x squared goes to 0 as x gets big, because you're dividing by bigger and bigger and bigger numbers. That should be a 2x squared, not just x squared. So in particular, your horizontal asymptote is always the ratio of the leading terms, but may not be the ratio of the leading coefficients. 7x squared grows fast, but 2x to the fifth grows much faster. So as x gets bigger, the bottom is going to grow faster than the top, and it's going to shrink the whole thing to 0. So g of x, which is 7x squared plus 1 over 2x to the fifth plus 8, the horizontal asymptote here is just 0. It shrinks the whole thing down to 0. Now contrast that with the other possibility. What if the top is growing faster than the bottom? So what if I have a function h of x, and it's 3x to the fourth minus 2 over 19x plus 7. As x gets really big, we can ignore everything but the first terms. But even when I ignore those terms, I'm going to end up with 3 over 19 times x cubed, and that blows up as x gets big, and actually goes down as x gets negative, because it looks like a polynomial. It's the end behavior is still, did I say horizontal asymptote or end behavior? I said the horizontal asymptote is always the ratio, if it exists. Because in this case, whatever my function looks like in the middle, by the end, it's going to look like this. And that has no horizontal asymptote. Because there is no horizontal line that guides this function as x gets very, very big, positive or negative. All right, one more topic. Can we build the formula of a rational function by looking at the graph? So here's a graph It's going to have an x-intercept at 3 and an x-intercept at -2. It's going to have a vertical asymptote at -1 and a vertical asymptote at +2 and a horizontal asymptote at -3. I should have done this from the beginning, but it's not a bad idea to only draw your horizontal asymptote on the very outsides. And let's say it looks like this. Yep. Turns around, goes down, comes down. Oh, it has to turn back around because there's no x-intercept in this area. And it's gonna go like that. There we go. That's what my graph looks like. So I want to build a formula, and to build a formula, we need the x-intercepts, the horizontal asymptote, the vertical asymptote, any holes. Should I put a hole? Let's do it. Let's put a hole right here at 5. And it would be nice to know the y-intercept as well. But again, that's hard to find unless you have an extra piece of information. So I can at least build everything except the y-intercept part. It's a fraction. It's got some x-intercepts. It's got one right there at x plus 2, and close to x equals -2, it looks like a parabola. So I better stick a power 2 on there. It's got another x-intercept at x equals 3. That one looks like a line, so I'll leave it as a power 1. It's got a couple of horizontal asymptotes. It's got one at x equals -1, so I'll put an x plus 1. And it's got one at x equals 2, so I'll put an x minus 2. And now I notice that it's got up at the top of this vertical asymptote, it's on the same side, right? They're both up arrows on either side of the asymptote. So that means the x minus 2 term has to have a squared. And that's good because the degree on top is 3, the degree on bottom is 3, and that means I'm going to get a nice horizontal asymptote right there at -3. -3/1 or -3. This is a possible formula, but so is -6 times x plus 2 squared times x minus 3 all over 2 times x plus 1 times x minus 2 squared, because the ratio of those coefficients is still -3. But these two formulas are actually identical. And the y-intercept is actually already decided, because in order to find a y-intercept, we need that missing piece of information. Well, in this formula, the horizontal asymptote is the missing piece of information. The horizontal asymptote will determine what the y-intercept has to be. Let's find out. I'll use the top formula. It's f, so we'll do f of 0, which is 3 times 0 plus 2 squared times 0 minus 3 over 0 plus 1 times 0 minus third, which times 4 is -3 all over 1 times 4, which is 9. That's y-intercept. So I could have given that to you at the beginning, but I didn't have to. Knowing the horizontal asymptote gave you that missing piece of information. All right, that ends the video. Thanks for watching.